Okay, good morning. This last example involves a concave mirror. So, in doing a concave mirror, again, you start by making your principal axis just like before. Again, make this as straight as possible. Again, and then choose a point that would serve as your center of curvature. So I will choose this point here. So that will be my center of curvature. And then again, I will use a compass, a drawing compass. And because I chose that as a center of curvature, that means that is where I will anchor the compass, the drawing compass. So something like this. And then I will have to choose the distance of the curvature from the mirror surface, right? And I can do that by using a ruler. Um, Let me just fix the ball pen that I'm using for the compass. So from the ruler, I can just measure any curvature that I have here. So maybe I will choose 1, 2, 3, 4. I will choose 4 inches. Okay. So I'll just measure this to that to be 4 inches. And from there, I can again make my curve. So make sure this is at the center, like so. And then as smoothly as possible, make your curve. Right? And then we are going to use the concave side. So this side, we are going to use this side. So, and again, since I noted that this here to here is 4 inches, so therefore I have to mark the halfway point, and that halfway point would be somewhere here. That would be my focus. So this is the focus, and this is the vertex here. Okay. So again, the part where you made the curve using a compass, mimicking the surface of a sphere is important. You cannot just make any curve. You have to base it on a real sphere. And again, even this is not accurate because in the real world, you have to make the surface parabolic. But, you know, spherical surfaces are approximations of parabolic surfaces. So this is good enough for some examples. Okay, so now after that you have to choose a case. You have to do 5 cases. In this case, for just an example, I'll choose just one of the cases, which is case number 3. So this is concave mirror case 3, and that case is when the object is between F and C, between the center of curvature and the focus. So somewhere between, somewhere here, maybe here, maybe here, maybe here, as long as it's in between the two. But just so that it's easy to spot, let me pick the exact center of the two. So the exact center of the two will be somewhere here. So that's where I'll put my object. And then I will now decide the height of the object. So for the height of the object, let me pick something that is very short, like half an inch. So from here to here. Or maybe 1 inch because it's really difficult to draw. So that's your object. And again, your object is always an arrow, right? So what do we know from here? So, well, we know that the F in this example, the focal length is here to here. But since here to there is 4 centimeters, 4 inches when we set our compass, therefore here to here must be 2 inches, right? And then we have to know the distance where we put our object. So if this is 2 and that is 4 and this is placed exactly between these 2 points, so this must be 3 inches. So that must be 1, to 3 inches. So this should be 3 inches. Okay. And then remember class that for a concave lens, concave mirror rather, concave mirror, the focus is positive. So this is positive. And the object is obviously also positive because positive means in front of the mirror. So remember, this is in front of the mirror because we are using this side as the reflecting side, not the convex side. Right? So that's positive and positive. And then how about the height? Well, we set that height to be 1 inch. And again, just to emphasize, that's also positive. That means the height is upright, meaning it's drawn upwards, not downwards. Right? And from here, we can now do ray diagramming. Right? So last time we did calculations. This time we do ray diagram first before the calculation. So the first ray is the FP ray. FP ray is again a ray that is parallel and then passes through the focus. So therefore, from the top of the arrow here or the object, I'll draw an incident ray that should reach the mirror surface. And after reaching the mirror surface, it should bounce back such that it will pass through the focus, like so. And then the next ray is the V ray, which is a ray that is coming from the top that hits the vertex, right? Coming from the top that hits the vertex. Top hits the vertex. And then for some of you, you might say, okay, Satoy, V-ray is it will go through the vertex and it will not change direction. No, that's for the lenses because, common sense. Lens allows light to pass through. So the light rays will just pass through. But this is an opaque material. So opaque materials will reflect the light back. So it should be reflected. So it's unlike the example for the lens where the light ray passes through the vertex and it goes straight without bending. In this case, it will be reflected, but you have to judge this angle and it will form the same angle. And the best way to do that, in my opinion, is just mimic this one. This is 1 inch, right? This is 1 inch, the object. So now locate where that 1 inch is on the other side like that. And from there, you can make your line from the vertex, like so. Okay? That's the V ray. And then now I have the FP ray. FP ray is a ray that's coming from the top, passes through the focus first, reaches the mirror. Once it reaches the mirror, it gets reflected such that it becomes parallel to the mirror. So if you want to be, accurate about this, you measure here, you mark there, and then you measure here, you mark so that it's completely parallel. But for me, I'm just going to estimate this like so. And then finally, you have the CC ray. The CC ray is from the top, hits the C. But if you notice, if you have the top hits the C, notice it will not reach the mirror. So we'll leave it at that. So we'll not draw that one. And I'm just going to fix this part because this arrow here, wamana gitiwas. So I'm just going to mark that there. And then now you can clearly see that the light rays meet here somewhere. And therefore you form an image here. And again, since the object's foot is on the principal axis, the image's foot should also be in the principal's axis. Just since this form the top of the object, this should form the top of the image there. Okay, so now we evaluate the lost. Where is the location? Well, the location of the object is between F and C. But where's the location of the object? of the image. It is beyond C. Lapas na sa C. So this is beyond C. Now, how about the orientation? Well, you can clearly see that this object, this image here is inverted. So it is inverted. How about the size? Well, this is the object, that's the image. You can clearly see that the image is bigger. So it's bigger. Then how about the type? Well, I can see real light rays hitting the mirror, real light rays meeting here. So this should be a real image. And in fact, I know that's a real image because it's formed on the normal side. Normal side meaning, again, if you have a mirror, we are expecting that if light rays come from here, they should be reflected on the same side. And since the image is formed on this side, then that's the normal side, that's real. If the image is formed way at the back of the image or inside the mirror dimension, then that's an imaginary or virtual image. Right? So now we have the loss by using ray diagrams. Now let's try to achieve that by using mathematical equations. So again, first I will have to solve for the Q, and then I will solve for the H prime. And then for the Q again, we will use the mirror or lens equation, which goes the inverse of the focal length is equal to the inverse of the object distance plus the inverse of the image distance, right? From there, I want to solve for one. I want to isolate 1 over Q. That's 1 over F minus 1 over P. I want to join this into one term, so that would be FP and then 1 over Q. But I don't want to solve 1 over Q. I want to solve Q. So again, Q is just the inverse of 1 over Q. So if you take the inverse of this, you also take the inverse of that. So this is FP over P minus F. And finally, now I can solve because I can now substitute. F is, well, 2 inches times P is, well, 3 inches positive, divided by P is 3 inches minus uh, F is 2 inches. And then from there, I can calculate 2 times 3 is 6 inches squared, because you don't just multiply the numbers 2 times 3, you also multiply the units. Inches times inches, inches squared. And then 3 inches minus 2 inches is 1 inch. And therefore, remember, inches squared is just inches. Duha ka inches. And there's an inch here, so the inch here and one of the inches will cancel out. So that leaves you with 6 inches. That's the Q. Remember, it's positive, right? It's not negative, it's positive. Now, how about the H prime? Well, H prime over H is equal to negative Q over P. Take note that the negative there is already inherent. So it's already there. So don't remove that. So if I want to solve for the H prime is just negative Q over P times the H itself. So negative Q is, as we have solved here, 6 inches, which is positive 6, divided by P, which is 3 inches, times height, which is 1 inch. So from there, you will have negative 6 inches squared over 3 inches. And again, the inches here and the inches here, the inch, the inch here will cancel out with one of the 2 inches unit here. And then that gives you the H prime finally to be negative. See? That's negative 6 over 3, negative 2 inches. Okay? So now let's take out the loss. Well, what is the Q? The object location, it's 6. But we know that here to here is 2. Here to here is 4. So 6 must be beyond C. So it's correct, beyond C. How about the orientation? Well, that is the sign of the height, object image height. The sign of the image height is negative, so therefore it's inverted. How about the size of the image? Well, I know that the object is 1 inch in height, but the image as calculated is 2 inches in height, so it must be bigger. So correct. Now, how about the image type? Well, that is the sign of the Q here. So if you look at the Q, it's not negative sign. It doesn't have a negative sign. Negative sign means it's a virtual image, but it has a positive sign. That means it's a real image. So there you have it. Using ray diagrams or calculations, we were able to get the same results, which is location of the object of the image is beyond C, the orientation is inverted, the size is bigger, and the type is a real image. And in fact, class, again, if we were using a parabolic curve, we would get this perfectly. But since we are not using a parabolic curve, there are certain errors. So for example, if you measure the Q, which is 6, if I measure here, it's not quite 6 inches, right? It's 5 point something because of the error in the curve. And if I look at the height, which is 2 inches, here it's almost 2, but not 2 inches. So there are some errors, but again, those errors are just because of the inherent error in the curve because we are not using a parabolic curve. And again, it's difficult to use a parabolic curve, so we are contented with using a spherical curve. For all intents and purposes, it mimics the same results as the mathematical one to a certain degree and to a certain accuracy that is tolerable. So that's why we use the spherical mirrors. Okay, so I hope that guides you in how to make your performance tasks. So basically, you have to do the ray diagram, you have to do the mathematical calculations, and you have to make sure that both the mathematical calculations and the diagrams kind of agree with the result to a certain degree. Okay, so that would be all. Thank you.